Dear colleagues, let me present to your attention the results of the research named Analytical Evaluation of the Performance of High-Loaded 5G IoT Ecosystem Functioning. The speaker is Viacheslav Kovtun. The motivation for this study arises from the increasing prominence of 5G IoT ecosystems in mission-critical domains such as industry, energy, transport, and public safety, where the reliable aggregation of data from multiple sensor networks under high load condition essential. Exciting analytical models often fall short in capturing the full complexity of such system, either by oversampling the network topology or by neglecting key technologies features of 5G, including any scheduling, discontinuous reception, hybrid automatic repeating request, and pocket fragmentation. So those limitation is in the focus of our research. Recent advantages in the modeling of 5G IoT ecosystems reflect growing interest in analytical approaches capable to characterizing complex network behavior. Those approaches require a layered analytical perspective where individual service models operate under distinct scheduling policies and quality of service constraints. Despite those advancements, a gap remains in developing integrated mathematical models that simultaneously address radio layer dynamics, pocket fragmentation, resource contention, and service layer processing. Those gaps underlies the need for a unified analytical framework which our research aimed to address. The object of this study is a high-load 5G IoT ecosystem characterized by the interaction of multiple sensor networks, which a 5G base station under dynamic and resource-constrained conditions. The subject is the development and application of analytical models for performance evaluation, incorporating mechanisms such as NR scheduling, pocket fragmentation, and other 5G-based machine learning methods adapted for telecommunication. The aim is to construct a robust mathematical framework capable of successive predicting key performance indicators, including response time, blocking probability, and system identness within realistic operational scenarios. This study considers a 5G IoT ecosystem comprising multiple sensor networks that interact with a GNB base station through adaptive radio resource allocation. Two operational modes are defined: time division mode, where the traffic is actively transmitting, and traffic control mode, enabling resource optimization and energy efficiency via DRX technology. Each sensor network consists of devices that generate requests and receive responses from the either local edge servers or external cloud service. Communication is coordinated using NRE scheduling, random access channel, and buffer status reports, while data integrity is maintained through HRQ mechanisms. The model assumes high-load conditions where the probability of endless neglect and data flows are continuous. The key performance metrics of our mathematical apparatus include the average response time for device in network, average processing time at the local or external server, average waiting time for GNB resource assignment, probability of request blocking at the GNB, and probability of no pending requests in the local buffer. At the slide 7, we can see the structure of the 5G IoT ecosystem for aggregating information flows from the sensor network, which is formed as a statement of the research stage. Slide 8 presents the formulas to calculate the average waiting time for GNB resource for the sensor network and the formula for calculating the success probability, which are formed in the basis of the mathematical apparatus presented in the article. The slide 9 presents another important parameters which are formalized on the basis of the proposed framework. It means average slot duration and another the probability of arriving an empty base station queue. Slide 10 presents the formulas for calculating the parameters that describe the pocket fragmentation process. I mean the formula to calculate the n-error and average time. Also, we can see the formula to calculate the minimum transmission time. To assess the adequacy of the proposed analytical model in the described high-loaded 5G IoT ecosystem, a structured three-stage verification was conducted. At the first stage, the model was benchmarked against classic queuing approaches, which are widely used for traffic analysis in the communication systems. At the second stage involved selecting a representative empirical data set which captured end-to-end latency and radio parameters across varied urban scenarios. The third stage focused on evaluating the model's predictive capability using the RTT metric under real-world traffic conditions. Figure 2 presents a comparative analysis of average round-trip time estimates derived from the proposed analytical model, the classical queuing models, and empirical measurements extracted from the MoMLeT datasets, which captures delay dynamics in operational 5G and NB IoT environments. The results demonstrate that under light traffic conditions, all three models yield similar outputs, reasonably matching the observed data. But at higher loads, the proposed model exhibits a slight underestimation in the RTT values, but continues to outperform both classical models, which maximum error margin not exceeding 20%. Figure 3 presents a three-dimensional surface plot demonstrating how the average response time in the high-load 5G IoT system is affected by two interrelated protocol-level factors: the degree of pocket fragmentation and the length of the RX included delay. The figure reveals a nonlinear surface where increasing the fragmentation degree initially leads to a reduction of response time due to improved retransmission efficiency and better adaptation to channel variability. However, the improvement diminishes as fragmentation grows extensive, indicating an optimal operation range. In construct, the DRX delay introduced a consistently negative impact, which response time increasing shortly at TD grows, especially when the system operates with low or moderate fragmentation levels. This interaction highlights the importance of balancing every energy-saving mechanism like DRX, which the responsiveness required in real-time IoT servicing. Figure 4 illustrates how the response time in 5G IoT ecosystem evolves under the combined influence of two parameters associated with the adaptive frequency hopping, the dwell time on a given frequency and the temporal duration of transmitted packets. The resulting surface shows that moderate increases in the dwell time initially reduce latency as they minimize the frequency switching overhead and stabilize channel quality. However, as dwell time becomes extensive, its positive effect plateaus and eventually revires, especially for the large pockets sizes that accumulate additional delays due to prolonged channel retention and contention. So the analytical evaluation confirms that the proposed model provides an accurate and structurally adequate representation of a higher loaded 5G IoT ecosystems. As shown in Figure 2, the model reliably approximates empirical RTGT values recorded in the real networks. The Figure 3 demonstrates the model's sensitivity to protocol-level parameters such as DRX delay and pocket fragmentation. The response surface reveals a clear trade-off where increased fragmentation improves performance up to optimal point, while the DRX latency introduces significant nonlinear degradation. Figure 4 further highlights the impact of adaptive frequency hopping, showing that dwell time and pocket duration interact in non-trivial ways to influence delay. Those results confirm that the proposed model captures complex adaptive behaviors often neglected in the classical approach and enables precise prediction of performance metrics across a range of practical development scenarios.